C.4, linear recurrence relations. In this part, we will find the solution of Fibonacci numbers directly. All right? Because nobody can guess this formula, right? Nobody, no matter how smart he or she is, no way to guess this formula. So for that reason, we need to find the solution. We need to do a lot of logical reasoning to find the solution. Yeah. All right. First, let us recognize the type of recurrence relation we have here. Yeah. It has a long name. Yeah. Second order linear homogeneous recurrence relation with constant coefficients. So that is the complete name of this type of equation. Yeah. Let me explain all the terminologies. First, easier part first. Yeah. Let us look at the equation first. A sub k equals capital A times A sub k minus 1 plus capital B times A sub k minus 2, with B not equal to 0. Yeah. First, it is a linear recurrence relation. Linear, because all the sequence numbers takes the linear format. Linear means the degree, exponent degree is 1. Okay? Linear, 1. Yeah. Nonlinear. Here, let me give you the nonlinear case. If any of the sequence numbers not taking degree 1, nonlinear. Okay? Yeah. So very simple. For example, if I write this way, A sub k equals A sub k minus 1 squared plus A k minus 2. Yeah. I only need to make one of the sequence numbers square form. Nonlinear. Yeah. Here we are very lucky. So all the sequence numbers take the linear form. Yeah. All right, so that's the linear. Second, constant coefficient. Yeah, coefficient. Capital A, capital B, both fixed constant numbers. Constant, yeah. So we have that, yeah, with constant, yeah. Then, second order. What do you mean second order? Right? Yeah. Look at the subscripts of all these sequence numbers. The highest subscript, K, highest. The smallest subscript, K minus 2. What is the difference? The difference is 2, right? 2. Yeah. Second order. 2 corresponds to second order. So that's the reason that we call it second order, not first order. Yeah. Here, let me explain why B is not allowed to be 0, because if B is 0, it becomes first order, right? Yeah. The B term is gone. Then you only have A term. Then the difference is 1. So it will be first order linear recurrence relation with constant coefficients. All right, so the last terminology, homogeneous. What do you mean homogeneous? Yeah, here, let me tell you non-homogeneous case. All right, so you will get the idea. Yeah. All right, so here, yeah, let's just do a little more. Yeah, for the Fibonacci, capital A, capital B, both 1, and it is simplified to this one. Here, let me just use this example. If I add another constant, C, constant C, then it becomes non-homogeneous. The reason is because you have a, non-sequence term, right? Non-sequence term. So non-homogeneous. Yeah. If we have a constant term, yeah, non-zero, yeah, this C, if it is not zero, non-zero constant term, then it becomes non-homogeneous. That simple. All right? Okay, yeah. Now, so you understand why we call this type of equations such a long name. Yeah. Next, let's solve it. All right, so now our question is like this. We need to find the solution. Now, here, some of you may still remember actually you solved this problem in discrete math. Discrete math. So there is one section for this type of questions. So you can solve it. Yeah. Here, let me just repeat that whole procedure. So let me also provide you all the details. Now, if you still remember how to solve it in discrete math, that would be great. Yeah, but I guess maybe small portion of you still remember. Yeah, most of you may, almost forget all the details. Now, let us look at the solution. Let us take a special view on the sequence. Yeah. Solution sequence, right? Our goal, find the solution sequence. A sub k sequence. Yeah. The first thing, we want to guess the structure of the sequence. If we can guess the right structure of the sequence, then it will be much easier. So you can see the guessing work extremely important in problem solving. Yeah. All right. Here, how about this guess? T to the kth power. Can we guess A sub k takes t to the kth power? You may feel it's not easy to make that guess, right? Yeah. Here we use the geometric sequence. It may not be easy to connect to geometric sequence, right? How do you explain that? All right, so here, let me use this way to explain it. All right. Let us consider first order homogeneous, linear homogeneous recurrence relation with constant coefficient. Yeah, let's consider that. Right? Yeah. A sub k equals A capital A times A sub k minus 1. How to find the solution of this type recurrence relation? Pretty easy, right? Yeah, because you keep multiplying A capital A. Yeah, every time you keep multiplying capital A, so A squared k subscript k minus 2, and so on. All right? Yeah. Eventually, can you get the form A to the k? Yeah. Little a sub k equals capital A to the kth. Yeah. Is this corresponds to the geometric sequence? Yeah. Here you can see the reason we make this guess, because if we solve the first order linear homogeneous recurrence relation with constant coefficients, our solution takes the geometric sequence. Now we move from first order to second order. So we just try to make a extension. Is it possible the geometric sequence structure can still be used for the second order linear homogeneous recurrence relation. All right, so we want to try it. Yeah, we may fail, but first let us try it. We may have a chance to be successful, right? Yeah, so let us try it first. Yeah. First, we ignore the initial condition, yeah, because we have to make the sequence follow this initial condition, but it will make the solution harder. So first, let us forget about that initial condition. So we try to make solution as easy as possible. We only consider the main part, the linear recurrence relation part. Yeah. All right. Now, question. Yeah. We want to find the solution in this form. So let us just plug into that recurrence relation. So we should have this equation. Then we do cancellation. Simplify the equation. So we get this one. T squared equals T plus 1. We can also simplify to this form. Looks familiar, right? Yeah. We solved this equation before, quadratic equation, right? Golden ratio, we know the solution. Golden ratio. Yeah. Actually, we know there are two solutions. For the golden ratio, we drop the negative solution, but here we have no reason to drop the negative solution, right? Yeah. Because here, the T is not necessary the golden ratio, right? Yeah, not necessary the golden ratio. So we have no reason to draw negative solution. So we should write those two solutions out explicitly. T1, T2, two solutions. Okay, yeah. All right, so after that, next, we want to put it back to our recurrence relation. T1, T2, they should satisfy our original recurrence relation. All right, yeah. So here, let us put it back. All right. The first one, T1, if we plug in back to, yeah, actually T1, right? So this one, we make AK equals T1 to the kth. Yeah. All right, yeah. So we get this equality. All right, equality. It must be true. Based on our solution, it must be true. All right, that's for T1. Second, T2, this time A sub k equals T2 to the kth power. All right, yeah, must be true. Both must be true, right? Yeah. So we get a lot of improvement. A lot of improvement. We get two special solutions for our original recurrence relation. But the problem, they're not satisfy the initial condition. Definitely not, right? Because first, they're not integer solutions, right? T1, T2, they're not integer solutions. So no way any of them satisfy the initial condition. But don't worry, we will fix that later. We have a chance. We need to use some creativity to connect to the initial condition and solve it. Yeah. All right. Question. How to use two special solutions without the initial condition to get a new solution with the initial condition. Yeah. So here the new question we need to answer is this one. Yeah. our starting point, we have two special solutions. Our goal, we need to find a new solution. New solution we can build on top of those two special solutions. Okay? Yeah. But we need our new solution satisfy the initial condition. So that is what we need to do at this point. Yeah. All right, so next question. Is there a special way to combine two solutions? Yeah. Because what we can use, the closest thing, we can use two special solutions. Yeah. So to start from two special solutions, to get a new solution, we want to combine two special solutions. Yeah. So that is the new idea to make progress. All right, so let's go to the next step. All right. Here, in order to combine, so I want to introduce a math concept that can help us combine two special solutions. The concept is called linear combination of two variables, x and y. Have you heard of that? Linear combination concept. Linear combination. So what's that? Two variables. That is defined by capital A x plus capital B y. This form we called linear combination of two variables. Capital A, capital B, both constants. Yeah. Any constants we can put there. Yeah. So later we will determine these two constants. Yeah. But now we have we know what should we go the next step. Next step. Linear combination. Yeah. Now let us get back to recurrence relation. Yeah. All right. Here, we use the linearity property of the recurrence relation. Remember, we see that linear term before, right? That means our recurrence relation has the linearity property. So we should take advantage of that, right? Yeah. Now, let us take advantage of that. Apply the linear combination concept to create a new form of the solution. This one. How about that? This is a linear combination, right, of two special solutions. The linear combination of two solutions is also a solution. That is the important property we have by taking advantage of linearity property of the recurrence relation. Yep. The linearity property results in this new property. All right? Yeah. So that means this whole representation is a new solution. We can plug in back to our original recurrence relation. You can check. It must be true. It must be true. You can verify it. It must be true. Yeah. Here, I do not need to do the verification. Yeah. Because it's pretty simple. Yeah. All right, next. How to determine these two constant, capital A, capital B, for the Fibonacci numbers. Yeah. All right. We just use two initial values. So that part should be pretty straightforward. Yeah. So the remaining, we determine capital A, capital B, pretty straightforward. All right. So let's do it here. Yeah. All right. For initial condition, when n equals 0, we should have the first initial condition, A0 equals 0, right? Little a 0 equals 0. That means capital A plus capital B equals 0. Yeah. After simplification, yeah. That means capital B equals negative capital A. Yeah. The second initial condition, we plug in after simplification, but we replace B by negative A. And factor out A, yeah, we know its value is 1, but we can simplify this part, factor out A, then two numbers subtraction, simplify it, square root of 5, root 5, so you get capital A equals 1 over root 5. Yeah. So then capital B, negative 1 over root 5. All right. Then, now we are ready to go back to our original formula, but use our golden ratio notation. Yeah. Phi, 1 minus root 5 whole thing over 2, negative 1 over phi. Yeah. We did that before, so we know it is correct. Yeah. Finally, now A sub n equals 1 over root 5. Take that capital A out. Now, parenthesis. First solution coming from T1, phi to the nth, minus second part from T2, yeah, negative 1 to the nth over phi to the nth. That's exactly the formula for the Fibonacci numbers we're familiar with. Yeah. But this time it's not from guess, from lot of computation, lot of logic reasoning. Yeah. All right, so that's all we have for part C, and we finish all 4 videos of part C.